So for the last 2 weeks, I've been away from home. So last week I lived and studied at the scientific campus near Kaluga, where I was preparing for the All-Russian Physics Olympiad for school students. This week I spent 4 days competing in the Olympiad in Dolgoprudny, including the arrival day at the MIPT university campus, 2 competitional days, and the departure day. So on the first day, as usual, we had the experimental round working with laboratory equipment, and on the second day there was the theoretical round where we solved physics problems. So this Olympiad was for 7th and 8th grade students, and it brought together winners of regional stages from all across Russia. So for example, in our room, when we were, there were 2 students from Voronezh, and one from Kaluga and one from Yakutsk. From my region, 2 students qualified to participate, a girl from Obninsk and me. So we are both 8th grade students. So for me, this was my first experience participating in a final stage of such a high-level Olympiad. So this is the most challenging physics Olympiad for 7th to 8th graders in our country. So the tasks are very extensive. For example, on the first day, the experimental round, I submitted about 13 pages, mostly consisting of measurements and graphs. And on the second day, I handed in submitted 22 pages. Handed in 22 pages with solutions to theoretical problems. So the first round lasts 5 hours and the second one lasts 4 hours. So there is almost no time to write drafts and very little time to double check your work. So it is excellent practice for gaining competition experience. So you need to learn how to quickly understand a problem, develop a solution strategy, perform calculations efficiently, and present your solutions clearly. All of this done by hand and by handwriting. So now I would like to give a brief overview of the problems that we were assigned in Dolgoprudny and practice explaining their statements and solutions in English. I somehow translated these problems. This is of course not as professional as the statements we were given at Russian. However, this is the first problem. This is the first problem of the theoretical round of the Olympiad, and it is really nice mix of statics and mechanics. So even though this setup looks quite intimidating or scaring at first with multiple cables and pulleys, most participants actually managed to solve it because here the idea is not as complex. So we have a strange loader machine that uses a system of 3 inextensible cables and pulleys to lift and move a part. So a loader itself can move horizontally, and through the pulley system, this motion translates into vertical motion of the load. So the task is broken into 3 parts. In the first stage, the loader moves, lifting the part while the cart is stationary. Next, the cart is moved into position, and the third is that the loader moves again to lower the part onto the cart, while cart is stationary as well. So we're giving parameters like target height capital H, that is the height of the cart, the cart floor height h small, and the width of the part A and the speed v for both the loader and the cart. And from there, the problem asks us to find the minimum initial distance between the cart and the part, so the loader can lift it to height h capital. So that is the minimum distance L capital. Determine how far the cart must be moved so that the part ends up exactly inside it during the third stage. Then want to calculate the total loading time while all stages happen one after another, when this process is sequential. And finally, we want to find the minimum loading time, the minimum possible time, if the loader and cart are allowed to move simultaneously in the last stage. If the cart has a distance L initially as well. So the key insight of the problem is understanding the constraint from this cable system. So as the cables are inextensible, using the forces equations, we want to notice that when the loader moves horizontally by some distance, the load rises vertically by half as much. If we would look more precisely at this system of pulleys. So this kinematic relation drives the entire solution. So it is a classical problem when you translate a mechanical setup into displacement relations. So we want to track here how these motions are linked, and at the end we want to optimize this process. So once we spot that 2 to 1 ratio, the rest of the solution becomes surprisingly clean. The minimum distance L equals to twice the H capital, and then the problem is becoming quite obvious. So the most complex task here is to track how horizontal motions and vertical motions of the part are linked. Let's look at the second problem of the theoretical round. This in the plank. So this is another statics problem, and that is a classical static problem. But now the focus here is an equilibrium of forces and torques in the system with a compound pulley. So what is going on here? We have a horizontal plank of length L capital with 3 masses, M1 on the left end of the plank, hanged on a string, hanging on a string on the pulley. Then M2 hangs through the hole in the plank on the string as well. And L3 hangs on the right end. So the strings are connected to a compound pulley with 2 different radii, R capital and R small. And everything is in equilibrium. So all string segments are vertical and the plank is horizontal. And the system is at rest. And the problem asks us to find the mass M3 that keeps the entire system balanced, determine the normal force N1 acting on mass M1, and the normal force N2 acting on mass M2. So the key idea here is to carefully apply the torque balance first on the pulley, because the pulley is in equilibrium, it is static, it is not moving. That means that we can write the torque balance for the from the pulley and then for the whole system. And to determine these normal forces, N1 and N2, we want to use the force balance for each mass. So a crucial step, the first crucial step is to use the torque condition for the compound pulley, and then express everything in terms of the given parameters. So as we wrote the torque balance from the entire system, as we got the relations of these tensions into, so as we write the equation for torque balance in the compound pulley. We get the relation between the tensions in two strings, and from there we can write torque balance for the entire system, as we know the tensions in two strings. So expressing this algebraically leads to the third mass M3 that is not known. We can express this from the M1, M2 are capital and L capital. Yeah, and also an important note that the Planck's mass is small. Yeah, and as we got the M3 mass, we can find the normal reactions N1 and N2. There we can express them from the from the force balance for each mass. So it also eventually it gives us a consistency condition for equilibrium. So, by the way, that is a classical equilibrium problem, a static problem. We combine force balance and torque balance. Then we want to track tensions through a compound pulley. This problem is also quite tricky part to track tensions in a compound pulley, because that is not two different pulleys, that is just one pulley that is compound. And we want to we want to manage extracting these unknown forces and constraints on the system. So this problem is a bit heavy algebraically inside. However, conceptually, it's all about setting up the right balance equations and working with them, as well, what's this word?
Algebraically?
Algebraically working with them correctly. This is, just the mathematical problem. The next problem, the third problem, is hydrostatics problem. It combines buoyancy, equilibrium, and geometry. So it is more experimental in spirit, because we are given a graph of immersion, depth versus time, and we want to extract physical parameters from these two curves of which this graph consists. So what's the setup of this problem? We have a hollow buoy made of identical cones connected joint base to base, and with a total height h capital. So a small weight is attached, so the buoy floats vertically in water. Then water starts slowly leaking inside at constant rate, while air escapes from the top. A sensor measures how deep the buoy is submerged. This is the immersion depth h of t that we are given. This graph that we are giving, the data from the sensor inside, so this sensor measures how deep the buoy is submerged until it eventually fails. So the problem asks to determine the total height h capital of the buoy, the rate v at which water volume increases inside, the mass m of the buoy with the load, so the mass of the entire system of the buoy plus this weight, I forgot the word, to this small weight. And then we want to determine the maximum and minimum differences between water levels inside and outside the buoy. So the key idea here is that the process is slow. So at every moment the buoy is in equilibrium. That means that the increase in weight due to incoming water is always balanced by an increase in the buoyant force. And this leads to a relation between the rate of sinking and the cross-sectional area at depths h small. So this slope of this graph shows directly the area of the buoy at the height. So from the graph, the slowest sinking corresponds to the maximum cross-sectional area. So when the scope is minimal, the area is maximum, is max, yeah. So this happens halfway the buoy at the point roughly 49, about 49 centimeters. So this gives us the H capital, the total height of the buoy equals roughly 98 centimeters. And using the slope at the moment, we can find the volume and flow rate. That is the speed as the authors of the tasks referred to it. That is roughly 1055 centimeters squared per minute. And from the initial immersion depth at this point, at t equals 0, we determine the total mass m equals roughly 20.6 kilograms. Finally, for these 2 points, the maximum difference occurs at the very beginning, when no water is inside yet, because at any next moment, this level is getting smaller and smaller. So the maximum difference occurs at the very beginning, so it is, by the graph, about 27 centimeters. This delta y max is 27 centimeters. And the minimum difference happens when the system becomes symmetric. So water levels positioned symmetrically inside the buoy. And that is roughly at 2.8 centimeters. So in short, this is an example of the problem, and it is a great example of the problem where a graph encodes physical information that we want to decode from the graph. And also the geometry of the shape is essential. And by the way, in my solution there are 2 pages of just geometrical notes because we want to calculate the size of the triangle that creates this cone. And to make this, we're using some geometry because we know that this apex angle of the cone equals 90 degrees, so it becomes a bit more simple. So this problem is less about heavy calculations, is not as algebraically complex as the previous one, and it is more about correctly interpreting how physics shows up in the graph. Next, the last problem of the theoretical stage, of the theoretical round, is about electric circuits plus thermodynamics. So it is centered around the thermistor. So that is the nonlinear element, that is the resistor whose resistance depends on temperature. So what is going on here? So we have a circuit with 2 ideal batteries with voltages U0 and 2U0. Centered, resistors R and 3R, and a thermistor, and also an ideal ammeter. Emitter. Yeah. So initially, at the initial moment, both switches are open. So first, switch K1 is closed, and the thermistor temperature stabilizes at 70 degrees C. Then, without opening key 1, key 2 is also closed. So a new steady state is reached at a lower temperature, about 50 degrees, at 50 degrees C. And also the current at the at the initial moment was I1 equals 155 milliampere. So we want to determine the resistance R, the voltage U0, and the new current I2 when both switches are closed. So we're also given the resistance versus temperature graph for the thermistor. That is unfortunately not in this PDF file. However, we are given a nonlinear graph and also a law for heat loss. That is the power of heat loss equals alpha times the difference of temperatures, T minus T0, where T0 is room temperature and alpha is a constant unknown coefficient. So the key idea is that in the steady state, we want to figure out why the temperature is not getting higher. Why is it steady? That is because in the power balance, because of the power balance equation, the electrical power dissipated in the thermistor equals the heat loss to the environment on these heat loss law. That is, by the way, Newton-Riemann-Riechmann's law for heat loss, and it equals to electrical power. So for each regime, we want to write this power balance equation of I squared times R by Joule-Lenz law equals to this Newton-Riemann law we are given. So it equals to alpha times T minus T0. So using the graph, we determined the resistance at T1 and T2, which are 850 ohms at 70 degrees and 250 ohms at 50 degrees. Then we expressed the current in the first configuration using this circuit. So we want to relate it to U0, R, and R1. R1 that we have determined that is 150 ohms. Then we want to write this power balance for both temperatures and want to whether divide the two equations to eliminate the unknown alpha or determine alpha from the first power balance equation. And we solve for R. This task is pretty obvious algebraically, so this gives us R equals to roughly 54 ohms, and the voltage U0 equals roughly 22.8 or 7 volt, something like that. And finally, when both meters are closed, this circuit simplifies. We want to use Kirchhoff's second law to find the I2 equals to roughly 142 milliampere. So this problem combines circuit analysis with this Ohm's law and Kirchhoff's laws with thermal equilibrium. This topic is very useful in multiple tasks, the thermal equilibrium of heat loss and electrical power, and it uses the thermistor's nonlinear behavior via the graph. So this is something like research theory problem. And the trick here is just realizing that we're not just giving the temperature. Its temperature is defined by the balance of electrical heating and cooling because of the temperature outside. So also we know that the room temperature, the ambient temperature is 20 degrees C, that we are always also given. So this is also a solvable task. This one, so this is the experimental round, the practical round of this All-Russian Maxwell's Physics Olympiad. So this is the first problem. That is the experimental thermodynamic. Oh, one moment. This is the experimental thermodynamics problem about cooling and evaporation. So it is less about solving equations algebraically, like the second problem of the theoretical round, and more about designing an experiment and extracting physics data physics known constant values from data. So what's going on? We want to research how hot water cools down in a cup. So two processes are responsible for heat loss. The first is heat transfer to the surroundings, as we've looked at the fourth theoretical problem. This also works on the Newton's-Riemann law, P equals alpha times the delta T, and also the water cools because of the evaporation. So it additionally removes energy. And to separate these effects, we want to perform two experiments. The first is that, using hot water, we want to record the dependence of temperature and mass and time on just hot water. And then we want to cool water covered with oil, and oil on the water blocks evaporation. So in both cases we measure temperature versus time and mass versus time, because we want to at first want to find which mass was evaporated, and at second we want to know for sure that if we cover the water with oil, it won't evaporate. So the problem asks us to describe a method how we determine the specific latent heat of vaporization L large. Heat of vaporization of water, that is a well-known value, that is the table value. And want to compare cooling curves with and without evaporation. How would the temperature, how the temperature would last faster, and then want to determine how the evaporation rate depends on temperature, and finally want to calculate L large. So the idea here is as well in heat balance. So the water without oil, energy is lost both through cooling and evaporation, and with oil there is no evaporation, so only cooling contributes. So by comparing these two cases, the power of heat loss with two cases, we can isolate the effect of evaporation, want to isolate the power of evaporation, and as we got this, it is the problem of determining the latent heat of vaporization is pretty obvious. So the evaporation rate comes from the slope of the mass versus time graph. This is the evaporation rate, and its slope what shows us the rate of this evaporation. And cooling rates come from slopes of temperature graphs. So the power of heat loss is the slope of this graph of temperature. And everything must be taken at the same temperature when the power won't change because of the Newton's-Riemann's law. And from the data, the here is the solution. So this is the equation for the first case, and that is for the second case. We covered with oil. So then some algebra that is not very complex, and then a lot of experimental data, a lot of measurements. So we want to estimate. So from the data, we are given the C of what the this word in English, the heat capacity of water. The specific heat capacity of water we are given, and we can determine the system heat capacity that is estimated as heat capacity of water times mass, the average mass of the water. And calculating L at several points gives us L capital equals to 2.6 megajoules per kilogram. And this is pretty accurate, how we say, approximation of a well-known data. So this value is well known of the of this value of water. So this is a fundamental lab style problem. So we want to separate physical effects, these overlapping effects, from using a setup of the experiment. We want to use graphs and its slopes with direct formulas. So we're combining all these, and also we want to extract a fundamental constant, a fundamental value in physics from experimental data. So when we are getting values that are well known, but we don't really know how they were get, it is a very interesting problem for us, and also it is great an example of a problem that can reveal hidden physics in such such a straightforward process of just cooling the water in the cup. Yeah, and next problem, it is less extensive. It is the experimental electricity problem about measuring the resistance of a wire hidden inside a tube. So the key challenge is that we cannot directly measure the full length of the wire or its resistivity of the material of the wire. We want to get them, but we cannot work with the hidden part of the tube. The key, we want to reconstruct these values indirectly. So what's going on? So we have a wire bent into a closed loop, part of which is visible along a ruler. So that is the open part for us. And we can place probes of a non-matter at different points on the visible part and measure resistance between them. So the task asks us to measure the probe resistance, record how the measured resistance depends on the distance d small between probes. We want to derive the theoretical dependence of r of d, and we want to transform it into a linear form. We want to linearize this, and linearization in physics is a very common and very important, is just crucial. A crucial skill. Linearization is just crucial in physics. As we transform it into linear form, we want to plot a graph and use it to determine the total length L capital of the wire and the resistivity. So the key idea here is that the wire forms a loop. So when we are measuring, when we measure the resistance of two points, there are two parallel paths, one of length d small and one of length L capital minus d small. So each path has resistance, and their parallel resistance is determined in something like that. So since they are in parallel, this is their equivalent resistance, and adding the probe resistance, we want to add the probe resistance, and this is what some participators forgot to do, to subtract the probe resistance, and that we measured, and to make it usable, to make this data hand manageable, we want to linearize it, and then this is this is the linearized expression where y is r minus r of probe divided by d, and all these other values of the linear form, that is y equals k times x plus b. Here are all these values, and then on the graph, we want to plot a graph and want to find the intercept and slope of this graph, using which we can determine the resistivity and length without measuring it directly. In short, this is an experimental trick to turn a nonlinear dependence into a linear graph and use these qualities of a linear dependence to find the values we want to find. So by the way, the cross-section area is given. So this example of how a clever modeling of the problem lets us measure something we cannot access directly. So, well, I'll wrap up here. This is the problems that were assigned to solve during the All-Russian stage of this Olympiad, of the final stage of All-Russian Olympiad. Well, thank you, Robert.
Yeah, thank you. Yeah, it's a very extensive exercise or lab or lab problems. I don't know what do you call this again? You call this this session that you
Experimental
participated
problems.
Experimental problem. Okay. Hey, I have a question for you. What is this word, or what are you trying to say? The heat capacity. What is a Russian word? Heat capacity of water. Because there's no not Russian. Heat capacity of water. There is. It's not capacity. I'll have to look the word up, but it's probably heat retention of water. I'm not sure exactly how we translate this, but
so in
but
Russian,
what is the word in Russian?
In Russian, that is the теплоемкость.
Yomkost. Yeah. Yomkost. Okay, I'll look it up. All right. Well, I'll send you some corrections in a day or so. But thank you very much for your talk. Yeah.